Hi.
Hello, everyone. Welcome to our session on algorithms and software today. My name is Thomas Richard. I'm an application engineer in the German branch office of MapleSoft. And we have three presenters today. Each one has 10 minutes, which is a strict limit. And we'll allow for 5 minutes of Q&A afterwards. And after all three presentations, there may be some time left for a general discussion. Thanks for joining us today. And I think our first speaker is Bertrand. Now I got that right. Bertrand Teguia Tabuguia from the University of Kassel, and he will present his results on the representation of non-holonomic power series. And I think it's part of his PhD thesis, which was supervised by Wolfram Köpf. Bertrand, please go ahead.
Okay. So thank you again for the invitations. I hope everyone can see my screen. Our talk is about power series representations of non-holonomic functions or power series. General purpose method for computing a power series of functions that do not satisfy linear differential equations are very rare in the literature. Most of the non-approach use the pattern matching model. And here we propose a general purpose approach that is able to find a recursive formula of the power series of most of these functions. For example, in Maple, when you want to find the power series formula of a given function, you usually think of using the formal power series package. However, with this function here, you will see that the output will be the input, just because the functions, the input does not satisfy a linear differential equations. This is needed for the formal power series method internally. Our package can be downloaded in this web page here. And I'm going to give the main steps of our algorithm. There are 3 steps, but the key step of this approach is the computation of quadratic differential equation. We also call it delta 2 finite differential equation, similar to D-finite differential equations. The thing is, instead of looking for linear differential equations, we look for differential equation still with polynomial coefficients, but we allow product of derivatives in the differential equation too. For example, in the case of tangent, here is the differential equations that we got. This is also homogeneous, and you can see the product of the first and derivative and the function here. For second, here is the differential equation, and for the log of 1 plus sine. And we are able to compute differential equations for many non-holonomic functions. This is the generating function of Bernoulli polynomials of order k. And if you try with our algorithm, you are able to compute a differential equation also for this type of function. Also, note that when the function is a holonomic expressions, the code is also able to compute the differential equation. So this computational differential equation kind of extend the usual approach used to compute holonomic differential equation, but just allowing some product when it's searching for differential equations. The second step is to convert the differential equation into a recurrence equations. This we have defined in our talk, if you have seen also in the accompanying paper, how we convert the differential equation to a recurrence equation. Here is the generating function of Bernoulli numbers. If you try to find the recurrence equation, here is what you get. And from this recurrent equation, we can deduce the necessary initial values. Also, we use the differential equation to find this, to know the number of necessary initial values. And then we can write the power series in this form. You will see that most of the general computer algebra system is not able to give a power series representation for this input here. And you will see that with this new approach, we are able to find recursive recurrence equations for Bernoulli Euler numbers or even Bell numbers, all these these sequences that could not be described by linear recurrence equation. For example, by using this recurrence formula here, we can write a simple code to compute Bernoulli numbers. Here we use it to define a simple code to compute Bernoulli numbers. And if you compute the first terms of the Bernoulli sequence, you can see with the built-in command that there is a coincidence. So we think that by using this algorithm, we are also able to compute Bernoulli to find recurrence equations involving such type of numbers. And as you can see, we can also compute with this simple code Bernoulli numbers or big Bernoulli numbers, but still the built-in command will be more efficient since we did not really care about the efficiency in this particular code. So this is another example of representation of power series. So as this function is not holonomic, but we can find a representation for this power series, and this can be used to compute truncated series of any order for this power series. So our code is also able to prove non-trivial identities because since there are non-holonomic expressions, trying to prove identities involving such functions is kind of difficult in general. And with this approach, since we are able to bring the zero equivalence problem to the power series computations, this becomes easier to check. For example, with these two inputs here, if you find the representation of F, then you get this power series representation. And this representation is the same representation found for G. This proves that F and G actually represent the same functions in the neighborhood of the computations. Here is 0. And moreover, with this, if you try to compute the power series representation of the difference of these two functions, our code is able to prove that this is 0. This is because the necessary initial values for this difference are all 0. When you look at the initial values here, if you have 0 everywhere, this is enough to deduce that the power series search for is equivalent to 0. So this is the brief summary of our presentation, and all questions are welcome. Thank you.
Wonderful. Thank you very much, Bertrand. This was a bit quicker than expected, so we have some more time for questions. I'll start with one about the complexity of your algorithm. Can you say something about the complexity of the proposed algorithm for finding quadratic differential equations of least order? For instance, how it depends on their order and on the degrees of the polynomials involved.
Yes, the approach we use is the method known as the ansatz with undetermined coefficients, and usually to compute the differential equation, the common method is to first fix the order, but also iterate on the order and the order of the polynomial and the order of the differential equation. But this is not what we do. So we have defined some class of functions, and in our iteration product of we do not fix the order of the polynomials. So the degree of the polynomial, only the degree of the differential equation is fixed. This product of derivatives are computed by a derivative operator that we have defined for any given functions, and this reduce the complexity, because usually with those who with the approach that consists of giving the iterate on the order and the degree of the polynomial, there are 2 loops needed to implement such an algorithm. But here we use only 1 loop to compute the differential equation, and this is why our implementation is rather faster than the common method.
Yeah, obviously. Very good. Okay. Next question is about the sequences of numbers that arise in the representation of the non-holonomic functions. For instance, you mentioned Bernoulli numbers and Euler numbers for tangent of z or for secant of z, respectively. Did you encounter any other number sequences from combinatorics, such as Stirling numbers, for instance? did you see any general pattern or?
This is something we are thinking of doing next. So use this algorithm to see how which kind of sequence we encounter, if this can help to maybe find new relations between or new recurrence equations, or even what is already known in the dictionary, in the literature. So this is just this is future work in this from this algorithm.
I see. We're very glad to see your future work as well, perhaps in a future conference. Okay. Yeah. Regarding implementations, did you encounter any specific differences or problems when implementing in Maple and Maxima?
What could I say? I think the difference could be, first of all, I will say the code is faster in Maple. And the second thing, but I think my only issue in Maple was the fact that as to have these initial values, when you know the number of initial value that you need to find to give the power series formula, you usually have to compute a certain truncated series. And the only issue in Maple is that this number sometimes is not the right indicator of the truncated series to be computed. So we have to check often, but only from that there is no big issue. The code was just straightforward from what I've already done in Maxima.
Mm-hmm. Yeah. So you are trying with an increased truncation order to check.
Yeah.
Okay. Yeah, makes sense. Mm-hmm. Thank you very much.
Okay.
Are there any other questions? We're a bit ahead of time and not under any time pressure. Okay, that's not the case. So let's thank the speaker. Thanks, Bertrand.
Thank you.
And for our next presentation, we have the pleasure of having Maya Chartouny from France, of the INRIA Research Institute, speaking on an algorithmic approach to the algebraic parameter estimation problem. Welcome, Maya.
Hello, everyone. My name is Maya Chartouny, and with Thomas Cluzot and Alban Quadrat, we worked on the algorithmic study of the algebraic parameter estimation problem. Let me first begin by giving a simple example. If we consider that you have a sinusoidal signal, which is a times sinus of omega t plus phi. The question here is, can the amplitude, the phase, and the frequency be expressed in terms of x of t and its iterative indefinite integrals? This is a problem that has been studied for a long time in control theory and signal processing, and there is a lot of methods that deals with this problem, but we have treated the new approach developed by Fils and Serra Ramirez in 2003, and our contribution is the algorithmic study using computer algebra methods. So this approach consists in considering the ODE satisfied by the signal, which is in our case the equation in black, where A0 is equal to omega square, and then to take its Laplace transform. But first, let us recall that the Laplace transform of x can be denoted by x hat, and the Laplace transform of x prime is equal to s times x hat minus x of 0. So in the frequency domain, we have that x hat satisfies the equation in blue, where V0 and V1 are the initial conditions. So now if we recover V0, V1, and A0, we can then go back to A, omega, and phi. So we notice that we have a polynomial of degree 1 and 0 for V0 and V1 respectively. So if we derive once this equation, we can recover V0 and V1, and then we obtain this system. And now we have to compute their explicit expression. So, but first we notice that we have two polynomials of degree 2 and 3 in V0 and V1. So if we apply L inverse, we will get explicit expression in function of derivative of x, and we don't want that. We want to get expression in terms of integrals of x. So for that, we have to get negative powers of s. So we rewrite v0 as n0 over d0 by dividing by the good power of s. So we have n0 here is equal to v0 over s cube, and d0 is equal to 1 over s cube. Same for v1. And then we apply L inverse to get the following expression that contains convolutions. And since V0 is a constant, we have that V0 is equal to L inverse of N0 over L inverse of D0. Same for V1. We still have A0 that is unknown. So if we go back to the equation in blue and we derive twice the equation, we can eliminate V0 and V1, and hence we can recover A0. That we rewrite as n over d by dividing by the good power of s, and then we apply L inverse to get the expression in black. So we can go back to omega a and phi by using the formulas in blue. If we substitute x by the signal, we can verify that we have omega square in the above expression, and the others we can verify that we have x of 0 and x prime of 0. In general, we don't only see the signal, but we see a signal that is corrupted by a perturbation and a noise. So we have x of t plus gamma of t plus varp of t, where gamma is the perturbation and varp is the noise. And I insisted on the fact that we wanted to get integrals of x and not derivative of it. And that's because we want to filter the noise. So for this, we showed that if x is a generic solution of the ODE and 0 is a regular point of the ODE, then all the initial conditions and the coefficients aij can be expressed in terms of x of t and its iterative indefinite integrals. The non-exact case is still under development, but I will give an example. So if we consider that you have x of t plus gamma, where x is the signal a times sinus of omega t plus phi, and gamma is a bias, so it's constant. It's a constant. So applying the Laplace transform, we obtain the equation in black, where a0 is equal to omega square, v0 and v1 are the initial conditions. So we have here a new term that is unknown. And if we denote by q bar this polynomial, we want to eliminate gamma. So we calculate the annihilator of this polynomial, which can be computed by using elimination technique and Grobner basis methods. So we get the following matrix, and then we apply each operator to the equation in black, and then we can recover a0, v1, and v0, and then we proceed as before to compute their explicit expressions. And then we can go back to omega a and phi using the formula in blue. So in general, if we have a signal plus a perturbation in the frequency domain, we have that z hat satisfies the equation in blue, where gamma is this perturbation, and if we apply the Laplace transform to it, we will get a fraction in S. So the last term can be rewritten as two polynomials, one in S inverse and the other in S. So we are interested in the degree of the polynomial in S inverse. If we set P this degree, and we multiply the equation in blue by s to the power p to normalize the equation, we will get the equation in red. And after that, if we note q bar, the last term, we can compute its annihilator. We showed it's generated by P1 and P2. Then we apply P1 to the equation in red to get rid of the last term. And then we can proceed as before to compute the initial conditions. So if the degree of the polynomial P1 times s to the power p times sk are such that it is equal to p plus ek, where p is this degree and ek is the degree of sk, and 0 is a regular point of the ODE, then all the initial conditions and the coefficient of the ODE can be expressed in terms of z and its iterative indefinite integrals. We used a lot the package NOA in Maple, which is dedicated to the actual study of the algebraic parameter estimation problem. And here are some main commands and Maple package used. We developed a bit the package non-A by adding some useful function, and we have added several examples. Thank you for your attention.
Thank you very much as well, Maya. I'm also trying to copy the link from the non-R package into the chat panel. One moment, please. And we have some questions that I'll perhaps read first. Typically, these inverse problems are numerically very difficult and sensitive. Did you investigate numerical stability, for instance, of the inversion of the involved matrices S and the augmented matrix C, besides your symbolic and exact calculations where the problems do not arise?
Can you repeat the last part of the question, please?
Yes. For instance, did you investigate the numerical stability of the inversion of the matrices in your algorithm? For instance, there's an S matrix and an augmented matrix C that you mentioned in your full presentation. And did you investigate the numerical well-behavedness of this inversion besides your exact calculations?
We have created a function to compute the inverse, which take less time to compute the inverse of the matrix C. So it computes faster the inverse.
Okay. But did you also consider numerical instability besides efficiency?
No, we did not do that.
Okay, that's perhaps more of interest to engineers. Okay, nevertheless, thank you. One more question came up. Which classes of non-constant perturbations can be handled besides the gamma of t, that's constant gamma times t to the r times Heaviside of t?
For now, we have studied this class of perturbation, which is the standard one. Yeah, and it's still under development for other class of perturbation.
I see. Thank you. So unless there are any other questions from the audience, which seems to be no, that's not the case right now. So thanks a lot to the speaker, to Maya.
Thank you
for your presentation. And we're going to number 3, which is Linxiao Wang from Western Ontario University. Hello.
Hello. Hi.
And she will speak about computing the integer hull of a polyhedral set.
Hi, hello. So our work is about an integer hull algorithm for the polyhedral set, and this is a collaboration with Jorgen and my supervisor, Professor Mark Maramaza. So in this quick Q&A session, I'll just quickly introduce what our problem is and give an overall view of our algorithm. So what's a polyhedral set and what's the integer hull? So if a convex polyhedral set can be defined as a set of linear inequalities, of course here A is a matrix and X and B are vectors. And we're interested in computing this PI, which is the integer hull of P, that is the smallest convex polyhedral set that contain all the integer points of P. And this figure shows a very simple example. These blue lines, so it's the blue shaded area, can be described as a convex polyhedral set. But if we want to compute the integer hull, which means we want this red area, because you can see all of these points are integer points, and we want a smallest convex polyhedral set that can describe all of them, so which is the red area. So our problem is, given this blue polyhedral set, we want to compute this red polyhedral set. And of course, there are a lot of algorithms out there. First of all, it's very similar to integer programming. So any integer programming algorithm can be adapted to solve this problem. And there's cutting plane algorithms or branch and bound. They're all built for this problem. But a lot of algorithms would depend on computing all these integer points and then try to find the convex hull of them. But we can see that, so using this example, all these green dots are the integer points, but we don't really need all of them to describe the integer hull. We only need these ones on the outside, which means they're the vertices of the this red polyhedral set. So we only need these vertices. That would be enough to describe the integer hull. So we want to build an algorithm that we don't need to compute all the integer points. We only want to compute these ones. So apparently the complexity would be less because the complexity of computing all the integer points within a polyhedral set is the complexity is related to the volume of the polyhedral set. Of course, if the volume is large, if you want to compute all the integer points, the complexity would grow. So we want one that is the complexity is stable with no matter what the volume of the polyhedral set is. So we built this algorithm that would so that the complexity is not really depends on the volume. So here's the interface of our command that we submit as a command called the integer hull command, and the input would be a polyhedral set object because it's in the polyhedral sets package. So so you can give a polyhedral set, of course it's irrational, and you call our command, and then we will, so by default we will give you the integer hull in the V representation, which means we will give the vertices list and the array list. And the array list is to describe the unbounded polyhedral set. So for this one, this is the bounded, so the array list is an empty one. So we have all the vertices, that is the integer hull of this input. So of course, you can also choose the return type to be a polyhedral set object itself. So we will just return you a object that is the integer hull. So now I want to use this very simple example to describe what's the idea behind our algorithm. So this could be an input. So this is a triangle. So this is a 2D polyhedral set. So you can see that these vertices are all fractional points. So, but the integer hull, for the definition of an integer hull is all of its vertices are integer points. So our idea would be replace each of these vertices, fractional vertices, with integer ones, so that our result would be integer hull itself. So our first step would be a pre-process, because as you can see, if we see this this relation as a line rather than an inequality, you can see that there's no integer solution to this 3x minus 6y equal to 7, equal to minus 7, sorry. So there's no integer solutions to this equality. So first of all, we will replace any of the facets that have this type of feature, which means there's no integer, definitely no integer point on them. So we'll replace this red facet with a blue one, which means we'll push it forward, push it inward towards the center of the polyhedral set. And we have proved that there's no integer points in between these two lines. So which means even after the replacement, we won't really lose any integer points in this process. So we will, so in reality, we'll do it for any facet that does not have integer points. Then we would have a kind of a sort of a new input. And next is for each fractional vertex of the input, we find the closest integer points on each facet that is closest to the vertex, fractional vertex. So for each one, for the 2D case, we'll find 2 such points on the 2 adjacent facet. Of course, for this one, we will have to find them for each one of the vertex. So we will, so you can see that then, so the vertex plus the 2 integer points, closest integer points, would form a little triangle. And this is basically our idea of how we want our complexity. It doesn't depend on the volume, because we have proved in our paper and in our the new paper from the Maple conference that we can prove that the distance between the vertex and its closest integer points does not really depend on the intercept of the line. It only depends on the slope of the line, which means if you, for example, this blue line, if you push it outwards, which make the volume of input larger, it won't really affect the distance between these two lines. So that the area or the volume of these little triangles on the corners won't really change even if the input is larger. So our idea is to form these ones so that we only need to solve the integer Hall problem within these corners, because for the middle bulky part, we have to make sure that each of the vertex is already integer points, because that's what our previous step is doing. So we don't really need to worry about this part. This is already integer Hall. In the end, we only need to add this part to our final solution. So we solve the integer Hall problem for these little triangles. Since they're very small, we can easily use a brute force way to do it, or maybe later on we'll have other ways to do it. But currently we'll use a brute force way to do it, which means we find all the integer points within these little triangles. Then we find a convex Hall of them. So we find the integer Hall of each of the corners, and then we have this middle part which is already an integer Hall. Then we find a convex Hall of all these integer Halls. That would form our final result. So this would be our final result. So the input would be this blue polyhedral set, and our output would be this red polyhedral set with these red dots as the vertices. So this is the idea of our 2D algorithm. So our 3D is pretty much the same, but just a little bit more trickier, because for example, this is the input. And the first step is the same. We will do some pre-process so that every facet would have integer points on them. Then similarly, we find the closest integer points to the fractional vertices on each of its adjacent facet. So which is these black dots on them. So again, we will have these corners that we will need to deal with. So similarly, this middle part, which contains most of the volume, would be an integer Hall already. So we don't really need to deal with this part anymore. But what's different for the 3D case is if we combine these corners and the center part in the 2D one, it will cover the whole input, which means we're done. We just need to solve these parts, and that's all. But in the 3D one, we can see that these edge area is not covered, which means if we stop here, we will lose some points here. So we have to deal with this edge area, which is the blue area on the right-hand side picture. So that's also what contains some integer points. So which means we would need to solve an integer Hall problem for each of these edge area as well. So for these ones, apparently you can see that the volume of these blue ones would actually depends on the length of the edge, which means it kind of depends on the volume of the input. So we further partitioned into smaller area. So similarly, we find the closest integer points on the edge that is closest to the fractional vertices. And then we form this 3 parts of this one edge. So we know that this red part is the same. Again, it's the same that all its vertices are integer points. So we don't really need to deal with it anymore. We only need to deal with these 2 little ones on the corner. So we have to do this for each of the edges. So then in the end, we will just combine all the results from the corner and from the edge, of course, from the middle central part, and that would be our final result. So for the 3D part, when doing the implementation, I think the most tricky part is how to find the closest integer points to the fractional vertex on a 3D facet. Right? So this is a facet and it's in 3D. So so here we first, because we already have a 2D problem that solved the integer Hall problem, because finding the closest integer points is also a convex or integer Hall optimization problem. So we first make a projection from a 3D facet to a 2D space. So here we use the homonormal form to make the projection. The reason we use this particular way to make the projection is because it will keep the integer points, which means if it's an integer...
the 10-minute limit. Linxiao.
Okay, so anyway, so this is I think this is the most tricky part. So yeah, we use this way to solve it, and we use our 2D algorithm to help solving this 3D algorithm, and we also use the grid package for the parallel computing. And you will see benchmarks in our full presentation and the paper. So yeah, so that's it. So yeah, thank you.
Thank you very much. Yeah, we have some questions. Let's see. If we got it right, your implementation will extend the current polyhedral sets package in the next version, maybe 2022, right?
I hope so, because we submitted for it to be a command in the polyhedral set package.
Okay, and so will the plot command of that package will that be extended to support displaying those integral points, which it currently does not?
We didn't, but our command, you can ask it to output a polyhedral set, then you can use the I guess you can use the plot to plot the integer hall. Yeah, but we didn't really like extend it yet.
So the output will look like what you've shown on slides 9 and 10, I suppose.
Slides. This one?
Mm-hmm.
No, this I plotted myself, so it's not really just
Excellent. Looks different from the traditional plot output. Okay. Next question is how well did your algorithm scale when making use of the grid package?
Sorry, can you repeat that?
Yeah, how well did your algorithm scale when making use of the grid package? So what was the speed up factor?
So if we use, because if you see the benchmark, the time is already very small, like it's like a second or 2 seconds. So with 4 node, we can have about a 1.6, 1.7 speed up.
Sounds impressive. Good. And we have another question from the audience. Is this an example of what is called computational geometry? Very broad question.
Computational geometry, I guess you can call it, because we actually use some command from the computational geometry package to help in our implementation.
Yeah. The package is essentially linking Maple to the QHull library, to the external library. Okay, yeah, for speed reasons. Okay, yeah. Thank you very much.
Thank you.
Any further questions? Doesn't seem to be the case right now. You're welcome. And since we have only had 3 speakers today, there's still some time left for open discussion, roughly 10 minutes, I think. So if anything has not been covered, feel free to ask your questions right now. Yes, apparently everything has been settled. Every concerns have been addressed. So let's thank all the 3 speakers again. Thanks for joining us today, and feel free to gather in the lounge for social activities. And apart from that, this is ending our today's program, and we hope to see you all again tomorrow.